Welcome to the third example in the chapter of axial loads. The question reads, a pin-connected structure is loaded and supported as shown. Member CD is rigid and horizontal before load P is applied. Member A is an aluminum alloy with a modulus of elasticity of 75 gigapascals and a cross-sectional area of 1,000 millimeters squared. Member B is a structural steel bar with a modulus of elasticity of 200 gigapascals and a cross-sectional area of 500 millimeters squared. Determine A, the normal stress in bars A and B, and B, determine the vertical component of the displacement of point D. Okay, so to start off, we'll write down all this lovely information. So we have a bunch of bars in our question, but most importantly, again, I want to emphasize that this bar CD is rigid, right? So when it does deform, and this is very important later on, when it does deform, that is exaggerated, let's say it deforms like this due to this force P, it's going to be perfectly straight. Ignore like my drawing. It's going to be perfectly straight, right? No deformation whatsoever. This might be B prime, if this is B, and then this might be, obviously not scale and whatnot, this might be A prime, and this might be A prime, and this is A, right? And this is D prime. But my point is this is perfectly straight. So that's number one. Bar CD is rigid. Okay, the modulus of elasticity for bar A is given. It is 75 gigapascals, or 75 times 10 to the power of 3 megapascals. Modulus of elasticity for bar C, for bar B, is equal to 2,000 gigapascals. So 2,000 times 10 to the power of 3 megapascals. In terms of areas, we're given the area for bar A to be 1,000 millimeters squared. The area for bar B to equal 500 millimeters squared. The length of bar A is equal to 2 meters. The length of bar B is equal to 1.5 meters. And this force right here, P, which causes this bar to, or this system to deform, has a magnitude of 150 kilonewtons. So P is equal to 150 kilonewtons. And with that, I think we can move on to unknowns. This question wants us to find quite a few things. Unknowns. Okay, it wants us to find, number one, the stress developed due to this force and basically the system. The stress developed in bar A, the stress developed in bar B. What is the equation for stress? The equation for stress is F over A, right? However, and let's also put the deformation equation there as well. The play, I don't know. EA, right? EA. That's the deformation equation. Okay, what does it want us to find? It wants us to find the stress developed in bar A and bar B. And we're going to use this lovely formula to find it. But before we can find it, we need to find the force first. So we'll go through all that fun in just a second. So we want to find the stress in bar A, the stress in bar B, and we also want to find the deformation, the vertical displacement of point D, right? Because remember what we said, once this bar is deformed, let's say, for example, it's a huge exaggeration, but let's say it comes all the way down here due to this force P, right? Rotates like this. I want to find this vertical displacement of from D to D prime, right? And this we'll just call delta D. So I also want to find that. But that'll be later on once we find the stresses and once we finish that. Okay, we can move on to our free body diagram. Our bar kind of looks like so. We have our point D, our point A, B, and C. This I notice is a pin connection, so I'm going to have an X and Y component, CY, CX. I'm going to have a force acting upward, and now I'm doing a free body diagram of this bar CD, right? So I'm going to have this force, we'll call it FB. I'll have this force from bar A onto bar CD. I'll call it FA. And I also have the force P, right? And I know this is 150 kilonewtons. Okay, my goal is to find the force B and force A. Why? Because I eventually want to find the stress A, the stress of bar A and the stress of bar B. And to do that, I need the forces as indicated with the equation. I already have the areas, right? How can I go about doing that? Well, I'll just take a moment about point C, right? If I take a moment about point C, then this force goes away, this force goes away, and only the forces that I care about are involved, right? My given and my two unknowns. But come to think of it, we forgot the dimensions, but we can add them quickly. This is 1 meter, this is 2.5 meters, and this is 1.5 meters. If I take a sum of moments about point C, I'm going to get that I'm going to have a counterclockwise moment caused by the force FB, so positive moment. I'm going to have another counterclockwise moment caused by force A, and I'm going to have a negative moment caused by my force P, and I can even call it 150 kilonewtons. 150 times, let's keep it as kilonewtons, doesn't matter. Multiplied by the distance away, so 5 meters, right? If I simplify this equation a bit, I'm going to get that 1.5 meters times FB plus 4 meters times FA is equal to 750 kilonewtons, and this is my equation 1. Right? I have one equation, or two unknowns in one equation, so I need another linearly independent equation to solve for my two unknowns. How do I do that? Well, I do a deformation analysis. And we'll call this actually deformation diagram. Okay, so should we copy this one? Actually, no, we're not going to copy it. We're just going to start from scratch. Let's say, for example, this is my point C, right? Does not change. This is my point D. This is my new point, D prime. Let's say due to this force P, it caused this entire structure to deform by this angle theta, right? We don't really care about the angle, but it deformed. And remember, it's perfectly straight, right? How about my points A and B? Let's say A is over here and B is over here, right? Let's just confirm, or the other way around. B is over here, A is over here, right? Therefore, let's assume that B prime is over there and A prime is over here, right? Hopefully this is making sense. Again, basically, we have original bar, we pull it down, and since this is a rigid bar, it is perfectly straight, right? Okay, beautiful stuff. Why the heck am I drawing this? Well, what's the deformation? And this is extremely exaggerated, obviously. What's the deformation of my bar, of each of these points, right? If I'm looking at it like this, well, my deformation for point B in this case would simply be deformation of B, right? This would be the deformation of A. This would be eventually what I want to find later on, the deformation of point D. Okay, beautiful stuff. Again, the whole point of analyzing the deformation is I want to relate different deformations with each other, right? How can I relate the deformation? In this case, I want to find the force B and force A. I know that the deformation of B will have the force FB within it, and the deformation of A will have the force FA within it, right? Because it's a force multiplied by an area divided by all that fun stuff, right? So I want to try my best to relate these two together. So I'll try. What can I do? Well, I see a triangle right here, and I see another triangle right here. Do I know this distance right here and right here? Yes, I do. Should have drawn it, but yes, I do. 1.5 meters from here to here, from here to here, and from here to here. This is 1 meter. This is 2.5 meters. Right? What I see right now is I can do similar triangles to relate my deformations together. And how that will basically work is I will relate this triangle, this, because I know this distance right here. This is just my deformation of B, of point B. My distance right here is 1.5 meters. And then similarly, I'll relate this triangle. The deformation of A, and from here to here is 4 meters. Right? So let me write that down. The deformation of A divided by 4 meters is equal to, this is the concept of similar triangles, the deformation of B divided by 1.5 meters. Beautiful stuff. Okay. Now I have a formula which I can derive all my fun from. Do I know the deformation of A? Let's branch off a bit. Do I know the deformation of A? Well, yes, I do. It's simply my force, Fa, multiplied by my length. What is my length? Well, it's just the length of my bar A, right? Divided by the elastic modulus of bar A, multiplied by my area of bar A, right? Do I know the deformation of bar C or bar B? Yes, I do. It's simply the deformation of B, or is it simply the force B multiplied by the length B divided by the elastic modulus of bar B multiplied by the cross-sectional area of bar B. And there is one thing that, I'm sorry if it was confusing, I may have explained this wrong, or I wasn't clear when I explained this. When I say the deformation of B, I don't physically mean the point, because I hope you see that once this bar goes down, the deformation of point B, let's say, for example, this bar does this, right? Let's say I am right when I say that this is the displacement of point B, but I hope you understand that attached to point B is this bar as well, right? So this bar will also go down, right? So the deformation of point B and bar B is the same, right? So that's why I'm using the length of bar B or the length of bar A and the elastic modulus and these properties. So please don't get confused when I'm using this terminology. Okay. I know the deformation of A. I know the deformation of B. I'm going to plug these two equations into this equation, right? And I'll also sub in some values. So let's actually call this equation 2. Now sub in values. Okay, so basically I'm going to get that my force A multiplied by the length of bar A, if I remember correctly, it's 2 meters, divided by the elastic modulus of bar A is 75 times 10 to the power of 75 times 10 to the power of 3 megapascals, multiplied by the cross-sectional area of bar A, which is 1,000 millimeters squared. And please do not forget, oh, that's incorrect. It's millimeters squared, because this is like a square cross-section, I assume now. But they gave me the value of the area. Don't forget this 4 on the bottom, right? 4 meters. Okay. This is equal to the deformation of B. So the deformation of B divided by 1.5. So FB multiplied by the length of bar B, 1.5 meters, divided by the elastic modulus of bar B, which is 2,000 megapascals, or seems we made a mistake all the way in the beginning. This is supposed to be 200. 200 times 10 to the power of 3 megapascals, because it's 200 gigapascals, right? Multiplied by the cross-sectional area, I assume it's 500 or 50. 500 or 50? There's a lot of mistakes, huh? Okay. Someone's tired, huh? Okay. 500 millimeters squared. And then please don't forget this 1.5 at the bottom, right? Okay, so if you work through both of these sides and calculate both sides, you're going to end up getting a simplification of FA divided by 100, I'll just write the full number, 100 million newtons is equal to FB divided by, or actually this one's 150, my bad, 150 million newtons, and then FB is equal to 100 million newtons, right? So basically this equation simplifies to this one, and this equation simplifies to this one once you calculate all your values. You can further simplify this equation to get your final equation from your deformation analysis, the equation you're going to use, and that is namely that FA is equal to 1.5 times FB. And finally, we can call this our equation 3. So from looking at the deformation of our system, we've successfully found an equation that's linearly independent from our original force equation, right? So now we have two linearly independent equations with two unknowns. We can easily solve for FA and FB. So that's what we're going to do now, but let's make this much smaller. So if I bring equation 3 and I bring equation 1, I'm going to end up getting, and I substitute them in for each other, I'm going to get that FA has a value of 150 kilonewtons, and FB has a value of 100 newtons, or 100 kilonewtons. Okay, am I done? Well, no, not yet. The questions asked you for stress, right? And now it's a very simple calculation. The stress is equal to the force, which we just calculated, over the area, which is given in the question, right? So we can do that right now. We can say this is 5, find stresses. Find stress. I know that stress is equal to a force over an area, so the stress for bar A is equal to the force for bar A divided by the cross-sectional area for bar A. Namely, that is, in this case, 150 kilonewtons. Convert to newtons, please. Divided by, I forgot the area for bar A, it is 1,000 millimeters squared. Right? For bar B, it's the exact same thing, but with its respective forces and respective area. .500 millimeters squared. So for your first part of the question, where it asks you to find the stress for bar A and B, you're going to end up getting a value for the stress of bar A to be 150 megapascals, and the stress for bar B to be 200 megapascals, and these are the stresses developed based off this force P acting on our system. Okay, are we done? Not yet. We want to find also the vertical displacement of the point D. And that sounds pretty familiar, right? We basically did that. We came up with this formula by doing just that, right? We looked at the displacement of point B, or bar B, like if you really want to look at it. But it's the same thing. But we looked at the displacement of point B, of point A, to find this formula. So all it wants us to do now is extend that thought process and now find the displacement of point D. So we can either compare this point D triangle with either the deformation of B or the deformation of A. We'll just do B. And we already have the calculation right here. It'll literally, we'll just steal this. once we need it, since we've already done it before. So it's fairly simple. So we'll call this 6. Find displacement, and we're going to assume the displacement is vertical. Displacement of point D. Okay, we want to compare this triangle and this triangle, right? This distance right here is 5 meters. This distance right here is delta D, the deformation or the displacement we want to find, right? Of point D. And then we already explained the one for B. Again, this is deformation of B, and this distance is 1.5 meters. By similar triangles, I can state that the deformation of B divided by 1.5 meters is equal to the deformation of D divided by 5 meters, we said, right? 5 meters. I can sub this, because I don't want to redo, I could redo the calculation, but I'm just going to sub this, where is it? This side of the equation, basically. I'm going to sub it in here, right? Because I already have it. I already did it before. And I'm going to isolate for delta D, but I'll do it one step at a time. So delta D is equal to 5 meters multiplied by delta B over 1.5 meters, right? I can sub this one in with this, and I'm going to end up getting delta D is equal to 5 meters multiplied by FB divided by 100 million newtons. I'm writing the full number because it looks pretty cool. You never get to deal with this much of fun, right? Okay, we're gonna sub in for FB, and FB right here is 100 kilonewtons. Times 10 to the power of 3 newtons divided by 100 million newtons. And just double check, everything's fine. Yep, 100 kilonewtons, 100 times 10 to the power of 3 newtons. And from this calculation, you're going to end up getting that your displacement, your vertical displacement of point D is going to be a value of 0.005 meters. So this distance right here, this displacement of point D is going to be 0.005 meters. And that is how you solve this beautiful problem. You found the stresses developed due to this load in bars A and B, as well as the vertical displacement of point D.